Okay, welcome to the video for our probability using counting project. So we're going to use permutations and combinations. That requires you to remember something of chapter 4, and the things that we need in particular are the formula for permutations and the formula for combinations, and remembering when to use each. Remember, permutations start with a P, like president, vice president, and treasurer. And in that case, order matters. It matters whether you were elected to president or treasurer. Combinations starts with a C, just like committees. Committees are just groups where order does not matter. If you're selected to serve on a committee, the order in which you were chosen does not matter. You're one of several equivalent members of that committee. We're going to use our calculators to actually compute these, but it's helpful to remember how this goes. Permutations are simply the product from n down to n minus r. So that factorial in the denominator basically says to take that n factorial in the numerator and stop when you get to n minus r. And similarly, combinations have an extra factor in the denominator of r factorial, and that's simply saying that you then have to divide out all the ways to order those r members of the committee. Okay, so let's take a look at our first question here. A 4-digit PIN number is selected. What is the probability that there are no repeated digits? Now, this is a probability question, so basically it's asking us to count two things. How many total 4-digit PINs are there? And that'll be our denominator. And how many 4-digit PINs are there with no repeated digits? That'll be our numerator. When we form that quotient, we'll get the probability. There's 10 possible values for each digit. There's 10 because it starts at 0. So 0 through 9 gives us 10 digits. Each of those 4 digits can be selected independently. So 10 times 10 times 10 times 10 is 10 to the 4th, or 1 followed by 4 zeros. So 10,000 potential 4-digit pins. Now, we want to count the number of pins that have no repeated digits. So we now need to ask a different question. And that is that whatever you choose for the first digit, you can't reuse for the second. So instead of 10 times 10 times 10 times 10, we're going to say 10 choices for the first, but you can't reuse that first digit for the second, so there's only 9 choices for the second digit. Now there's 2 digits that are taken out of use, so there's only 8 choices for the third digit. And now there's only 7 choices for that fourth digit because the previous 3 have already been used. So you can think of this as choosing without replacement. So we're not putting a number back when we're taking it. It's another way of thinking of this exact same idea. Now, we are basically saying that order matters when you're making a PIN. So 1, 2, 3, 4 is different from 4, 3, 1, 2 or something of that nature. So we're going to use a permutation. We're going to say that there are 10 choices for n, and we're going to choose 4 of them. So let's take a look at our calculator to remind ourselves how to do this. So I'm going to turn it on. I'm going to clear the screen. I'm going to go into I'm going to enter 10 first, then go into the math menu, go over to probability, down to NPR, which is our second choice, press enter, and then enter 4. And press enter. Now notice that this is the same thing as 10 times 9 times 8 times 7. So we could do it the long way, or we can use permutations to get to that same place. So we've counted, but what we really want to do, or what's still left to be done, is to determine the probability. And that simply means taking these two pieces of information, the total number of possibilities in our sample space and the total in our event space, and forming that quotient. So there's 5,400 possible pins without replacement, over 10,000, so that leads to about 50.4%, the probability that a randomly chosen pin will have no digits repeating. So we're now talking about a lottery with 48 balls, and we're choosing 6 of them. So 6 of them are drawn at random. And we're then going to say, well, if you match all 6 of those numbers, then you win $1 million. Of course, in terms of actually computing the probability, that $1 million doesn't tell us anything. The order of the number that the numbers are drawn does not matter. So that's important. The order that the numbers are drawn does not matter. So we're not going to use permutations, P standing for president. We're going to use combinations, thinking of a committee, just a group of numbers. And we are choosing 6 of them. So the question then becomes, in this lottery, so we're going to compute the probability that you win the $1 million prize if you purchase a single lottery ticket. So our numerator is going to be 1. There's only 1 out of the possibilities. So we need to count how many different ways there are to draw 6 balls without replacement, where order doesn't matter, from 48. So that's a combination. So we're going to say 48 choose 6. So let's see that in our calculators. So I'm going to enter the 48, go into the math menu, go over to probability, down to NCR. We're choosing 6, press enter again, and I see a ridiculously large number. I'm counting decimal places here, and I'm seeing 12,271,512 different possible ways, of which, if we're interested in using one chance to find that, our probability of making that $1 million prize with one guess is the reciprocal of that number, a very small probability. So now we're going to ask a similar question. So in the lottery from the previous example, if 5 of the 6 numbers drawn match the number that the player has chosen, the player wins a second prize of $1,000. So now we're asked to compute the probability that you win the second prize, again purchasing a single lottery ticket. So some things are the same. So as above, the number of possible outcomes of the lottery drawing is 48 choose 6. So that's the 12,271,512 different ways of drawing 6 balls from 48. In order to win the second prize, 5 of the 6 numbers on the ticket must match 5 of the 6 winning numbers. In other words, we must have chosen 5 of the 6 winning numbers and 1 of the 42 losing numbers. The number of ways to choose 5 out of 6 winning numbers is 6 choose 5, and that's 6 ways. And the number of ways to choose 1 out of 42 losing numbers is 42 choose 1, that's 42 ways. Thus, the number of favorable outcomes is given by the multiplication rule, the basic counting rule. We're going to multiply the 5 correct choices out of the 6 possible times the 1 incorrect remaining choice out of the 42 remaining balls. Remember, 42 and 6 add to 48, and there are 48 balls. So we're saying 6 times 42, which is 252. Our denominator is the same. It's the same 48 choose 6 that we computed before. But now our odds have increased, but not really by that much. If you look at the difference between these two, the only difference is the numerator is 1 when we have to match all 6. And down here, the numerator is 252. Now, granted, that means that our odds of winning the second prize are 252 times greater. But if you look at what that actually means, that's still a ridiculously tiny number. Here's a question that relates to card games. It says, find or compute the probability of randomly drawing 5 cards from a deck and getting exactly 1 ace. So in many card games, and I'm told that includes poker, the order in which the cards are drawn is not important, since the player can rearrange the card in his or her hand any way that she chooses. In the problems that follow, we'll assume that this is the case unless otherwise stated. Thus, we will use combinations to compute the possible number of 5-card hands. Now, order doesn't matter, so we're using combinations. There's 52 cards, and we are randomly selecting 5 of them. So the denominator, that is our sample space, is 52 choose 5. We're selecting 5 cards at random out of 52, and the order of that selection doesn't matter. This number will go in the denominator of our probability formula, since it is the number of possible outcomes. Now for the numerator, we've got to think about 2 different things. We've got to think about the number of ways to draw 1 ace, and then the 4 other cards, none of them aces. Remember, it says exactly 1 ace. So we're first going to count the number of ways of drawing 1 ace, and we're going to multiply that by the number of ways of drawing 4 other cards that aren't aces. So there's 4 aces in the deck, and we want exactly 1 of them. So that's relatively simple. Among those 4, we want to count the number of ways that we can draw 1 of them. Well, that's just 4, right? The 4 potential aces. Now, if you take the 52 cards in a deck and you take away the 4 aces, there's 48 cards that are not aces. They are the other cards that we can draw. And from those, remember, we're being dealt a hand of 4 cards. We're going to get 4 of those non-aces. Again, order doesn't matter. So from those 48 cards, we are drawing 4 at random. So that's the second part. That's the number of ways to select 4 non-aces. Now we use the basic counting rule, that's the same as the multiplication rule, to calculate that there will be 4 choose 1 times 48 choose 4 way to choose 1 ace, that's the first factor there, and 4 non-aces. So when we actually go through and do this, we need to, I'm going to leave that highlighted because that's what we want to calculate. So I'm going to turn it on, and I am going to first show you what 4 choose 1 is. And you say to yourself, what's going to be 4? There's 4 aces, and we're talking about choosing 1 of them. Let's convince ourselves of that. So there's 4. Now I'm going to use the arrow key to go up and grab that equation. And I'm going to change the 4 to a 48, which means I need to press second insert and type in, and then let's see, I'm going to arrow to the right and then back, 48. And I'm choosing, it probably would have been easier just to go back into the menu for this one, but that's okay. The remaining 4 cards are chosen from the 48 cards that are not aces. So I'm going to press enter. Then I'm going to take these 2 numbers. So I'm going to go grab that number. I'm going to multiply it by the 4 ways that there are to choose an ace. And I'm going to multiply that together. So that's my numerator. And the denominator is, and I'm going to go grab the combination again. I'm going to arrow back through it and change this to all 52 cards. We already know this number. We're computing it again. 52 choose 5. And now, just showing how you can do all this in your calculator, I'm going to grab the numerator by arrowing up and pressing enter. That's our numerator. We're going to divide it by the total number of ways of choosing 5 cards. And I'm going to ask it to perform that division. And amazingly, that's about 30%. So let's take a look at this. And it says that we're going to compute those 2 combinations in the numerator for the 4 aces and for the 48 other cards, choosing 4 of them. And then in the denominator, the total ways of selecting 5 cards out of 52. So just two more of these. Let's take a look at them. Compute the probability of randomly drawing 5 cards from a deck and getting exactly 2 aces. Now you might say to yourself, wait. Is this going to be as similar to the previous problem as you might think? So let's take a look at what was going on up there. In that previous problem, we said for choose 1 because we were only choosing 1 ace. My guess is that 1 is going to become a 2. There are still 48 cards that are not aces, but now we're going to be choosing 3 of those cards that aren't aces. Okay, just a kind of connecting where we were to where we're going. So it is very similar to the previous example. So let's take a look. So we're going to rewrite this with our probability statement. We want 2 aces in 5 cards. And so in the numerator, we're going to see, no great surprise, 4 choose 2. That's the way to choose 2 of the 4 aces. And then of the 48 remaining cards, we're going to choose 3 of those. So I'm going to highlight that. I'm going to highlight the previous question where we were choosing 1 ace and then 4 of the non-aces. Now we're choosing 2 aces and 3 of the non-aces. I'll also point out that the denominators are the same because the sample space is still the ways of choosing 5 cards out of 52. So let's put this in our calculator. I'm going to go up and grab as we did before. So I'm going to go and grab that and change the 52 to a 4. I'm going to delete that second 2. I'm going to go over to the 5. We're choosing 2 of those 4 aces. There's 6 ways to do that. That's 4 times 3 divided by 2 times 1. 4 times 3 is 12. 2 times 1 is 2. 12 divided by 2 is 6. We have to divide it by 2 because order does not matter. So we're counting the number of ways of ordering 2 things, and we're dividing that out. I'm now going to arrow up and select that 4 choose 2. I'm going to go back in and press insert after the 4 and make that, oh, I pressed a delete instead. Okay, 48, and I'm just going to go to the math menu, over to probability, down to the combinations, 48 choose 3. I'm going to take these 2 numbers, I'm going to arrow up and enter to get that first number. I'm going to multiply by the 6, which I just entered instead of arrowing up. I'm going to get our numerator. So our numerator is 103,776. Our denominator is the same. Let's get it again since it's relatively easy. I'm going to make that 48 into a 52 and we're choosing 5 cards. So there's the total number of ways that you can choose 5 cards. Let's go grab our numerator by arrowing up and then pressing enter. Let's divide that by our denominator, then press enter again to actually do the division. So when you randomly deal 5 cards out of a deck of 52, the probability of getting exactly 2 aces is about 4%. So let's look at the arithmetic here, exactly what you'd expect, and there's approximately 4%. Our last example is very similar, but now instead of talking about aces, we're talking about hearts. So in this question, it says, compute the probability of randomly drawing 5 cards from a deck and getting exactly 3 hearts. So remember that there are 4 suits and there are 13 of each suit. Okay. The solution is similar to the previous example, except now we're choosing 3 hearts out of 13. And if you take 52 and you subtract 13, I know I don't have to show this, but I seem to be showing this. 52 minus 13 gives us that there are 39 other cards. So there are 39 cards that are not hearts. So you might take a look back at that previous question and say, of the 13 hearts. We're choosing 3 of them. So you can imagine the first thing that we're going to look for in our numerator is 13, choose 3. There are 39 non-hearts and 2 remaining cards to be pulled. So 39, choose 2. So let's take a look at how that looks in our equation. We're interested in choosing 3 of the 13 hearts. So 13, choose 3. We're interested in choosing 2 of the non-hearts. So 39, choose 2. Now let's actually do that in our calculators. So we will go and grab one of these combinations and change the n to a 13 because there are 13 hearts. We're interested in exactly 3 of them, so I change that to a 3. There's 286 ways that you can pull 3 of the 13 hearts. We're going to now arrow up and ask the question, how many ways are there to choose 2 of the remaining 39 cards? So 39, choose 2. I'm going to press enter. I'm now going to go grab these 2 numbers by arrowing up and pressing enter. Put a multiplication symbol between them. Press enter again, and I'm actually doing that multiplication now. I'm now going to arrow up again. I seem to do this every time. And then change that 39 to all 52. I'm now computing the denominator, and we're selecting all 5 of those cards. Let's go grab the numerator by arrowing up and pressing enter. Let's now divide that by the denominator, all of our sample space, and see that there's about an 8% chance that you'll randomly select a 5-card hand with exactly 3 hearts in it. So 8.15% approximately. So combinations and permutations allowing us to answer questions about probability.